Discuss question number 26 from test 10. This is from thermodynamics. Okay, so 4-cylinder engine running at 1200 rpm. So speed is 1200 rpm. Power, brake power is 20 kilowatt. Okay, the average torque when one cylinder was cut is, so torque when one cylinder cut is given as 110 Newton meter. So obviously, so this is basically a test to measure the indicative efficiency. So when one cylinder is cut, the torque is measured to be the, so when the power with one cylinder cut is nothing but, once you know the torque and the speed is maintained constant, so its torque into omega is the power, which is nothing but torque into 2 pi n by 60. So it's 2 pi nt by 60 is the general formula for the brake power. Now let's use the torque when one cylinder is cut. We'll get the brake power and the one cylinder is cut. So 2 pi 1200 into the torque is 110 by 60. So this is your the brake power when, so this comes out to be 13.823 kilowatt. Now if you just recall, when all the cylinders are working, so IP1 plus IP2 plus IP3, which is the indicative power, plus IP4 is equal to the sum of the frictional power plus the total brake power, which is obtained at the output side. When one engine is cut, then it produces only the 2, 3, 4 produces the combustion results. Okay, so IP2, so indicative power will not be there for the first, so that will be equal to the friction power plus the brake power nu. Brake power nu when one cylinder, so this is, I'm calling brake power nu. So friction power is assumed to be constant because the speed is maintained constant. So if you subtract 2 from 1, I get IP1 as difference in the new, IP1 as the difference in the old minus the new brake power. So old is 20 when everything is running, that is 20, minus new is 13.823. so this comes out to be 6.177 kilowatt. So this is indicative power. Now what is asked in this problem is the indicative thermal efficiency. So the total, let's now calculate. So IP1, so IP2, IP3, IP4 will be all same because it's the average. IP3 is all same, so the total IP would be 4 times IP1, which is 4 times 6.177. so this comes out to be, let's use a calculator. So this comes out to be 24, let's call this as 6.8, so this comes out to be 24.72 kilowatts. So now I need to know the fuel consumption, because indicative thermal efficiency is ours. So indicative thermal efficiency will be your IP by the energy consumed, that is mass of the fuel consumed into calorific value. So I need to know mass of the fuel consumed. So calorific value is given 43. The mass of the fuel consumed is indirectly given as 360 grams per kilowatt hour. So that is 360 grams per kilowatt hour. Now obviously whenever nothing is specified, so that kilowatt hour is your brake power. So 360 into gram, for the gram I am converting in kg, by kilowatt hour, so I multiply with brake power. Brake power is 20 kilowatt, so this is kilowatt hour. So this value is 360 into 10 power minus 3 into 20 kg per hour. Okay, and I need kg per second, so I can just divide by 3600 kg per second. So this value comes out to be, if I cancel this comes out to be 2 into 10 power minus 3 kg per second is the mass of the fuel consumed. So let's take it here. So IP is 24.72 kilowatt. So let's put in kilowatt only, and mass is 2 into 10 power minus 3 kg per second, and this is 43 megajoules. So put 10 power 3 so that it becomes kilojoules per kg. So what is left in the denominator units is kilojoules per kg. kilojoules per second, and in the numerator you have kilowatts, so both cancel out. So final numerical value is 24.72 into 2 into minus 73 into 43 into 10 power 3, so that becomes 24.72 by 86 kilo. So that's just the ratio. It's 24.72 by 86. So this value comes out to be 0.28. So in percentage it is 28.74 percentage. So that is the answer for the indicative thermal efficiency. Answer is C. Option is C, 28.72. Thank you.